Saranya I'm currently a high school student in Springfield High School. It's near Philly, so it was a fun drive here. I was working with Dr. Lisa Rodenberg from Rutgers University and Mohsen Al-Halou, a PhD student from Rutgers University, to use machine learning to understand biodegradation of PAHs in Newtown Creek. So, first of all, as we all know, we have laboratory studies. These studies aim to predict what can theoretically occur in our environment, based on our controlled conditions and simulations. On the other hand, we have data mining, so using environmental data, doing data analytics on it, and this provides insights on what's actually happening in real time in the actual environment. So both of these methods, of course, are complementary and they give us a holistic view. Just to let you know, we're focusing on the data mining aspect in this project that I did. So for some background, Newtown Creek, it's a 3.8 mile long tidal creek that branches off the East River in New York. It runs between Brooklyn and Queens. It's currently a Superfund site in New York. One of the biggest contaminants are PAHs, or Polycyclic Aromatic Hydrocarbons. First question is, how did they get there? Well, several industries have left their mark on this region. Notably, we have petroleum refining, metal smelting and refining, and one of the biggest environmental events that happened here was the Green Point oil spill. So essentially what happened is, this disaster was discovered in 1978. There was a spillage of around 17 to 30 million gallons of oil. So there are, currently at this creek, there are two naval or non-aqueous phase liquid plumes that are at this Newtown Creek. Now we know that the larger one is primarily due to the disposal of unsellable products, but based on the timeline, we can kind of assume that the newer plume is from this Green Point oil spill. So the spill was one of the biggest sources of PAHs in the creek. Now PAHs are a big deal. They're hydrophobic in nature, means that they persist in the environment, and because they form as byproducts of carbon-based fuels, they can form from a lot of sources, which makes them widespread. Now they're not only persistent, but they're also known for being toxic, carcinogenic, and bioaccumulative. Also, these PAHs, there can be problems when you have alkylated PAHs as well, which are found in crude oil and such. So we wanted to analyze the PAHs and understand how they changed over time in Newtown Creek. So we used data from Newtown Creek's remedial investigation databases from the EPA. These include around 50 measurements of 50 different PAH compounds in over 1,000 samples of sediments. Now this is a big data set, but that's in our perspectives when working with things like Newtown Creek. So our data was split between surface and core samples. And the PAHs can be further broken down into 25 parent PAHs and then 25 alkylated PAHs. So first analysis we used was a positive matrix factorization method. This essentially identified the different sources of toxins. So specifically where the PAHs should come from. So the PMF basically gave us factors, which are pretty much like fingerprints as to see where the sources, what the sources are. While the model does identify a screenshot of basically what that source could be, we as researchers have to identify how many sources are present, which gives it kind of a little bit of error margin. However, these fingerprints only capture a screenshot in time, and we're left with understanding how do these fingerprints change over time and space. So there were 6 factors we had identified in Newtown Creek, specifically for the PAHs. So 2 of them were coal-related sites. And then one of them, the NC6 one, represents urban runoff. As one of the other significant sources. It makes sense due to the closeness to the highway, the amount of urbanization or industrialization near the creek makes sense for why that would be a factor. And the other 3 are from petrogenic sources. So that means they're related to petroleum. We found that one matched a profile similar to sources from crude oil, but the other two might be related to the potential green point oil spill, NAPL. So we wanted to analyze, so basically showing these fingerprints like in graphical format, we can see the distribution of different pHs in each source. Now, one thing I want to point out is the similarity between NC5, so factor 5 and factor 6, the bottom two, and this, because they're so similar in terms of like where is the abundant pH concentration and the distribution, we can kind of like think that they're from similar sources, so it's possible that both are from the green point oil spill. So the data we've been looking at has been from sediment data, but again, we're interested in looking at how these toxins have been changing over time. So we looked at groundwater fingerprints that would also probably contain the same particles from the spill. So here are some locations where the groundwater samples were collected, close to where the plumes are. And just a little bit of background, these plumes were like shut down in 1980 due to, with a slurry wall, and we just had to like consider that while figuring out where to get our sources of groundwater. Okay, so we ran a PMF model again for these groundwater sources, essentially to compare the sediment and the groundwater factors in our study site. So while comparing them, we found the groundwater had 3 factors, and as we saw earlier, the sediment had 6. But we found that the 3 factors from the groundwater matched 3 of the factors from the sediment, and specifically NC1, NC3, and NC4. Now these are the factors discussed from the plume, NC1 being from the older one potentially, and NC3 and 4 being from the green point oil spill potentially. So these matching properties can show that there's some kind of subsurface contamination, which is why we think it's these plumes. So while we were comparing these, there was something interesting we saw between, so in this third factor, between the groundwater and the sediment, there was a loss of ACE and COP in between the groundwater and the sediment. And this could have been from partitioning, where the chemical is like disappearing from the sediment and it goes into the water above, but that's not consistent with these results. So it's possible that, and this was our hypothesis, that these changes in the fingerprints were happening due to biodegradation. But something to remember is that even with contamination, the contamination may be changing over time due to biodegradation. So trying to understand this, so even if it's not biodegradation, trying to understand this will help us understand pHs over time. So like I mentioned, the hypothesis was that we're trying to see that the differences between the groundwater and sediment might have been from a biodegradation process. So to test this, we wanted to analyze a biodegradation metric to see the extent of biodegradation and correlate that with multiple water quality parameters found in the creek to see why was this happening and if it actually could have been happening. Our objective here was essentially to understand the process. So basically, from looking at past literature, we see that old studies use a biodegradation metric looking at the percent of total PAHs. But like I mentioned in Newtown Creek, there are multiple sources of PAHs. So when we try to get a percent of total, we get weird numbers like a couple 100%, which doesn't seem right when we see that there is a difference between that the sediment and the groundwater. So we saw that this measure probably wouldn't work for us, so we tried to make our own. Essentially, this was a non-negative least squares regression. It used values from the PMF fingerprints, Y being the fingerprint we're trying to analyze, and we have like variables from the other fingerprints. So we're holding all other fingerprints constant to see if the degradation of that target fingerprint matches with the profile of the creek. So we've measured 2 things, deg, which is like the degradation amount, and then we have a control variable. But if you look at this histogram, clearly that is not normally distributed. So it makes it really hard to run some statistical analyses on that. So that was one of our major problems. The data wasn't distributed normally or log normally. So we also found that there's a lot of like correlations between our dependent variables, again making it hard, and that's not accounted for when we're doing these analyses. So, when we're measuring it with that biodegradation metric. So we had to look into new methods in R. One of them, and these were like supervised machine learning approaches. One of them was a stepwise multilinear regression model to measure like significance between the correlation of variables. What was good about it is that this didn't factor in, it didn't require having a normal distribution. Same with the random forest algorithm, but this also helped us identify relationships between the dependent variables. So that was something we could account for using these two methods. And just like some more description on these, again, we could use this because we had our weird data distribution thing happening, but we could also use a ranked regression. So it gave us like the sign of the slope of the correlation. So is it a positive correlation or is it a negative correlation? And it could use AIC to determine if the correlation was significant. And that like narrows it down for us a lot, because if it's significant, that's the only things we're going to look at. And with a random forest, again, the distribution doesn't matter, thankfully, and that can help us better understand the correlations between the dependent variables in Newtown Creek. So how the random forest model works is it basically makes multiple trees or multiple connections between the dependent variables and keeps the ones that accurately predict the dependent variable and kind of adds on to that. What's good about it is it works for qualitative and quantitative, although we're focusing only on the quantitative. Okay, so we can use both random forest and the stepwise linear regression as our to create a biodegradation metric. And this was to tell us the extent of biodegradation. So some of the potential outcomes that could have happened before we did our analysis, we were thinking about this, is either aerobic degradation or anaerobic degradation. Now, Newtown Creek has like a distribution of where dissolved oxygen can get to, and we'll get to that later, but and we can tell if it's aerobic or anaerobic based off of correlations with creek mile, ammonia, phosphorus, and like nutrients in general, and total organic carbon. So, but then if we have random correlations, that tells us that there's a difference in the groundwater and sediment, and that's not because of biodegradation. So these are like the main variables we were looking at while looking at like degradation, or the correlations between our degradation metric. But we got data for all of these variables. So here are our main results. We're using both a random forest and a stepwise multilinear regression. Here we can see there's a positive correlation for the phosphorus, the total solids, and the total organic compounds. Now there's a negative regression with the creek mile. So in this process, we can see that there's the main variables we're focusing on again are the phosphorus, creek mile, the total solids, and the TOC. And there's a positive correlation with phosphorus, positive correlation with total solids, negative correlation with the creek mile, but positive with the total organic carbons. Now, much of this TOC can possibly be attributed to the hydrocarbon contaminants like oil. But what's nice about these forest plots is it shows us the ranking of correlations between variables, so we can see that we can see what's important and what's not. So this is a more detailed look at the variables for correlation. And we can also see, based off of the other variables we were analyzing earlier, with the old biodegradation metrics, and we can see that we have a better understanding of how what correlates between the biodegradation metrics here. So the thing to focus on here is the bottom row. You can see that there's variables. The variables that are significant are the only ones that are highlighted. Others are NS, non-significant. We can see that this profile shows there's an aerobic degradation. Now, like I mentioned, creek mile is important. Now that's because Newtown Creek branches off the East River, and the East River is actually what oxygenates Newtown Creek. So the further you go upstream Newtown Creek, the less oxygenated it is, and there's a lot of, and that's why if creek mile is important, that shows that there's, it's most likely aerobic degradation that's occurring in the creek. Now we also see that phosphorus is important. This divergence in signs from the other biodegradation measures might lead us to believe that that the old ratios are reversed. So that's something we're looking into. But yeah, so essentially we found the link between degradation ratios, nutrients, and the creek mile. It's the potential cause may be from aerobic degradation of the pHs. So next we're working on refining the existing model, having a better proxy to gauge like the redox status of the sediments. This may be possible like through metals. So we'll look into that. We're also going to we might be using PMF residuals to enhance the precision of our analyses, like the initial comparison between initial creation of that multilinear regression model might be further refined if we use residuals. So we're also looking into that. But there are a lot of unknowns, and I'd like to acknowledge one of our Rutgers undergrads who is working with us on this. And thank you for listening. I'd be happy to answer any questions.
So for your PMF model, so if I was understanding that right, it sounds like you need to know, to use something like that, you need to know the sources in the system already, and then it matches these samples like along the river to sources?
So, kind of yes, but also no. We don't even know exactly what those sources are, as the PMF model is going to help us better understand that. Yeah. But we do need to understand like how do the the PMF model kind of gets really bad once there's more sources than necessary, because it's like splitting the data up in too many ways. So we have to be able to identify when that shift happens to there's too many, like the shift between the right amount and too many sources. So that's the if you part is there 6 or 7 sources? So that's the part where you have to refine better. And one way we've refined it is using the AIC metric for significance on these models. So that's an error that could have happened in this process as well.
Okay.
So aerobic biodegradation is higher in these compounds, right, than anaerobic?
Yes.
Would your information be used then to identify areas where you would want to promote aerobic environments to help break down those compounds?
Yes, exactly.
Okay.
So that's getting to the purpose of the study.
Yeah, that's what I was curious about.
Right. So it's to see we have these pHs in the environment. They're obviously changing. What's causing the change, but also if we find that this degradation is happening with aerobic conditions, if we promote those aerobic conditions, we can better break these toxins down and then kind of get them away out of the environment. Actually, an initiative Newtown Creek is doing is adding aerobics, bubbling systems to get that oxygenation process there. You can hear it if you go to the creek. It's very loud and smelly, but it's working. So that's what we're trying to get to.
So I have a question. After 30 years of dredging projects, and PAH is always being my #1 issue, right? Who paid for your study? Because you had quite the lab bill looking at that data and the number of samples and what you analyzed it for. That was quite the bill.
So all this data was from the EPA's they have a remediation plan for Newtown Creek. They're doing this phase 1, phase 2, seeing changes over time.
Okay.
One was in 2005, one was in 2001, I think. And we're using that data to do our analysis.
Gotcha.
Yeah.
Okay.
Because you're at the beginning, this was all about data mining. So you're using data that's already available.
Yes.
Yeah, because you're looking at 200 to 300 samples.
Yeah. I don't know that samples actually.
Any further questions? Just a reminder, we do have a open session here from now until lunch, so all 3 speakers are here. If you have more questions and you want to keep discussing, feel free. Otherwise, lunch is I got a quick peek at the menu. It is Latin based.